Now in the previous lecture series we had learned that how we can analyze and design a pre-engineered building shell. Now in this lecture series I had told you that I shall teach you how you can design the portal truss system for pre-engineered building. This line may be somewhat confusing to you, but eventually I will explain everything to you. But before going into detail of this portal truss method, I want to give you a brief idea of another article that has been written on the internet. So the website is mgsarchitectural.in, and here there's an article written here. So basically some of you might be thinking that why we need to go to the steel structure for large spans instead of RCC structures. So basically the reason is the high strength to weight ratio. So RCC as compared to RCC, steel has much higher strength to weight ratio. So that is the reason why steel structures are used. And as he's saying that structural span larger than 40 meter can be regarded as a long span structure. The critical parameters becomes weight, deflection in the sway, and the foundation forces. So to control the sizes of the foundation and to make the foundation much more economical, we go for the pinned foundation. And on the top of the pre-engineered building structures also we provide this 550 MPa galvanum profile sheets. So you can Google the galvanum profile sheets, and so basically this is the galvanum profile sheet, and its strength is in the range of 550 MPa. The usual life of this type of sheeting is in the range of 5 to 10 years depending on the quality and the thickness of the galvanum sheeting. And most of the hangars are the structure where where the aircrafts are parked. So hangars are also made in the with the help of pre-engineered building system. So in this article he has explained that how he had designed this 42 meter clear span hangar for aircraft maintenance, and he had used the STAR software. And basic philosophy of rigid frame design is by adopting a fixed or pinned column based condition. So on the fixed we are offering the supports, reactions, and bending moment along all the 6 principal directions, whereas in the pinned we are only offering the reactions along the 3 principal directions. So design a foundation may become a nightmare, particularly in large span buildings when we are going for the rigid end conditions. So that is, here you can see that this is the fixed node here that has been modeled here, but this is the pinned base here. So the purpose of this article is to explain that how you can save the foundation, or you save the size of the foundation in the when we are going for the pinned reactions, and how basically the purpose is that how you can design a hangar structure. So on weak soil, designing foundation may become tedious task. Obviously when the soil is weak, the bearing capacity is weak, and when the bearing capacity is weak, the foundation sizes become very large. And to control this deflection, simplest way is to increase the geometrical property section size of the frame. That is about obvious thing that he has written here. And the best way we could find is to brace to the frame to control the excessive deflection. As I had explained in the previous lecture also, when we were designing the pre-engineered building structures, I told you that when the earthquake forces strike in the horizontal directions, it becomes very important to manage those forces, because those forces becomes excessively high. Along this direction the moment of inertia is very high. That is, this portal becomes itself the major factor of resistance for the forces along this direction, but along this direction there are very less forces that can be balanced. So to control the horizontal sway along this axis and to control the deflections, what we do is that we provide this the bracing along this direction also. So here he had given the various parameters, that is span is 42 meter, the length is 76 meters, and you should know that in the previous structure we have designed the span of 25 meter. So 42 meter is also not a big deal for you unless you had understood all the concepts and practiced thoroughly the example that we had covered in the previous lecture. The length is 76 meter and the base spacing is approximately 7.6 meter. The clear height is 10 meter. In the previous example we had covered the height for 10 meters, for 8 meters, and the wind speed is 50 meter per second. That is also not too high and not too low. Roof slope is 1 in 10, the one that we had already covered in the previous lecture. So this is the fixed base design. So here you can see the planning that has been done here. So basically this is the entry of the aircraft along this direction. So this is completely open. So to control the excessive sway along this and this, what the designer had did is that he had braced on the starting point and end point, so that if force strikes on the starting or either on the end, the whole forces managed itself here only, and very less forces are transferred on these portals here. And if some force gets transferred, we had also provided a bracing in the middle. You should note that bracings does not only activate when wind comes or when the seismic forces come, they also activates when there are excessive thermal expansions and contractions. If you remember your basic physics that you had studied in school, the change in the length, that is delta L, is equal to L into alpha into delta T, that is the length of the member into coefficient thermal expansion into the change in temperature. So those things do happens in the structures. Those things you should note that when for example, if let us say the length of the building is in the range of 90 to 100 meters, so and that building is in steel, the expansion and contraction in the case of severe temperature change may go up to 60 to 70 mm also. I am talking about the total length of the building. So that those expansion and contraction are not balanced just like that. They are either balanced in the form of the bracings, or in the case of the RCC structures, the extra stresses do come on the structures. So that is the reason why this expansion joints are provided. For the case of the steel buildings, expansion joints are usually not provided up to in the range of 90 to 100 meters, but when we are talking about 150 meters or 200 meters, we do need to provide the expansion joint in between. And in the case of the RCC building, it's not desirable that we go beyond in the range of, let us say, 45 to 50 meters. And it is also not like no building is designed for a greater amount of length than 50 meters. It is just like when we are going for the larger length of the building, we do need to take care of the thermal stresses, and we do need to balance them in our structure. So coming back to this point here, so we were discussing about the fixed base and the bracings. I hope the things are now clear to you after seeing this diagram, that how you can plan the bracing in your structure. This is also a very widely asked questions in the videos that how and where we can plan the bracing. So this is a perfect example of how you can plan your bracing. That is, you can provide your bracing in the starting point, in the end point, and in the middle point. And this is just a plan bracing that we are talking about. This is the plan of the structure. So when we are talking about the elevation also, the designer must have provided elevation bracing here, 1, 2, 3, 4, 5 and 6 number of points for the elevation bracing. So this is the typical portal that he has designed. So he had changed from 700 to 1000 into 6. That is this height is 1 meter, this height is 700 mm, and the thickness of the web is 6 mm, and the flange thickness is 225 into 10. That is 225 is the width of the flange, and 10 mm is the thickness. Here, when the forces are maximum, what he had done is that he had varied from 1275 mm here to 700 mm here, and the thickness of the web is 8 mm, and the flange width is 375 mm, and the thickness is 16 mm. So in our example, it was in the range of 1 meter. So obviously, when the span becomes large, the size should also become somewhat larger. And here he had provided a very big member, that is in the range of 1275 into 8. That is, the width of the web is 1275 mm, and the width of the flange 375 mm, the thickness is 16 mm. So this is the method with which the sizes are given in the pre-EB drawings. So you should know how to read this data. So these are the reactions that are coming on the structure, and the deflection is allowed in control. So see, these are the deflection that we are talking about. So vertical deflection here is 111 mm, and the horizontal deflection is maximum 15 mm in the along X and 47.8 mm along the Z direction. and these are the forces that we are talking about. You can see how much excessive bending moment is coming here. So 1651 kilonewton meter bending moment is coming, so that is excessively high bending moment that we are talking about. And here he had done the basic sizing and basic eccentricity calculation. So eccentricity is m by p, E is equal to m by p. So that is the basic principle that we had already studied in our college. So it comes out to be 4.03, and the length of the pedestal should be greater than its eccentricity. So L by 6 should be greater than E. So we can see that L is approximately 25 meter. So this type of foundation, he had proved that it is very unpractical and uneconomical. And so to avoid that, what he had done is that he had provided the pinned foundation along all the bases. So by providing pinned foundation, we can see that the sizes are almost same. The forces here, you can see that obviously when we are going for the pinned foundation, all the bending moments here are 0, and the reactions are same. Basically how you must be thinking how this excessive bending moment is coming on the bottom here, and how the whole bending moment automatically balance on the top, and on the bottom it becomes 0. So my question is the answer itself, that is the whole bending moment distribute on the top of the structure. No bending moment comes on the bottom of the foundation. So these members and all the structure must be so rigid that they should be capable of resisting all the horizontal and vertical and torsional bending moments on the top itself, so that no bending moment shall come on these 2 points here. So here it can be seen that obviously when we are designing the these foundation for the vertical reaction only, so here you can see that only this 398 kilonewton force is coming on the bottom. So it may gets increased to 450 kilonewton, let us say 45 ton, and this horizontal force will also contribute to the sizing calculation, because this horizontal force on the top becomes the bending moment at the bottom of the foundation. So this is also another important concept that that can be read in the soil books, that how you can design the foundations for the horizontal reactions. So he has just explained everything. So here you can see that obviously the vertical deflection become excessively high, as in the case of the fixed foundation. Here you can see that the vertical deflection was only 111 mm, so it almost becomes double here, that is 222 mm. So that is the thing, that are the pros and cons of providing fixed base and pinned base. So as per the code of provision, deflection allowed is h by 150, and all those calculations he had provided here. So he had also focused on that how you can provide this E bracing here. So here you can see that he has not provided this bracing here. No bracings are provided here, but basically what exactly is happening here, he is naming that it is an E bracing, and although it is an E bracing, but basically you should in your mind as a designer, you should understand how forces travel in the structure. So consider it just like a force that is acting here. Let us say 10 kN force travel here. So from this point it travels to this point, and from this point it travels to this point. So it goes on like this unless it diminishes, or unless it becomes 0. So this is the fundamental principle, that when we are talking about the very large spans, so here you can see that it is 76 meter span, so we should give force a path to travel. So if a force does not get a path to travel, it will become an obligation, or it will become a headache for you, headache for a designer to balance all those forces. So provide a good path for a force to travel, and you shall see that your structure becomes very much stable, and your structures becomes very much economical. So these are the basic fundamental things that are not taught in the colleges, and only experienced shall teach you, that how you can plan your structures well, and how you can make the forces in your structure travel in a good manner, so that no horizontal or excessive vertical deflections come in the structure, no obnoxious bending moments or no obnoxious torsional values comes in your structure, and your forces travel correctly to the foundations or either to the rigid members who have a very high stiffness that can take those forces. So the purpose of this lecture was to just to explain you that how you can plan your structures, how you can plan your bracing, what are the difference between the pinned foundation and what are the difference of the fixed foundation, what are the pros and cons. When we are, instead of fixed foundation, when we go for the pinned foundation, we do need to provide this bracing also, because excessive vertical and horizontal deflections are occurring in the structure. So all those things are here. You can see that deflection without raised eave, horizontal deflection become 4350. So it is nothing but an instability that is happening here. So 4.3, no member can deform by 4.35. So it is just more or less an instability that is happening here. So all those things, I shall advise you that design structures on your own, visualize the structures, go to the like whenever you see the steel structures in reality, observe those structures, observe the members and how they are made and how they are welded and what are the type of connection that has been given here. Steel structures are very beautiful structures in the sense that they give an infinite power to the designer, that you can make steel structures as much as steel structure the way you want. Because unlike in RCC structures, you only have those conventional beams, you only have those conventional RCC columns. But in the case of steel structures, it is not like you can make a simple I-shaped column. You can also make a portal column, or you can also make a column which is smaller in size on the bottom, more in size on the top, so that the costing becomes lesser for those type of structures. So there are many factors for steel structures that can be learned only by watching the steel structures in practical, practicing the steel structures, designing the steel structures. And so coming back to the basic fundamental of this lecture, that how you can design the portal sheds here. So this is a typical portal elevation that has been drawn here. So here you can see that what designer had did is that the span is approximately 20 meters that we are talking about here. So for span 20 meter, they had drawn the slope here also, and they have drawn this type of arrangement here. So in this type of arrangement, you can see that the members are drawn like this, and here they are provided the cross bracing, and then again the members are traveling like this. So and do not think of like the structure, think of like what happens when you are putting, suppose 10 kilonewton of force here. So basically what will happen is that instead of the bending moment, instead of what was happening in our structure here, so here if you remember, all the forces were becoming in the shape of the bending moment that we are talking about. So in this structure, what will happen is that all the forces will travel in tension and compression only. No excessive bending moment will come on any part of the structure. So these are the simple basic fundamentals that you should know while designing the steel structures. So in this example, what we shall do is that, because I don't want to repeat all the loading criteria and all the things that already has been explained in the previous lecture. So what I will do is that I shall keep all the dimensions same, so that your wind loading also remains same, and I shall change the structure to a portal shed structure, so that you can also learn and you can also see that how in this structure, when all the forces were in the shape of the bending moment, how it gets traveled in, how it gets converted into the axial forces and shear forces. So in the next lecture we shall learn how we can model this type of structure and how we can analyze and design it. So in the previous lecture we were discussing about how different type of portal frames can be made, and how this pre-engineered building, what exactly is a pre-engineered building concept. So here you can see one more example, that how basically what he had done is that he had made this whole system as truss structure, and these are the columns that he has made, and We shall see a model also. Before we change our model, I also want to explain you in stat that how things can be made. So this is one typical portal that we are talking about. So what designer had did is that he had just made this column as a built-up column with these two members, and by providing a tie and by providing this bracing arrangement here. And here also you can see that this is the truss arrangement that he has made here. And again you should notice that this member is now connected to this member, so the whatever forces traveling here, it gets traveled to this point and then it gets traveled to this point. So similarly it can travel all the way to the ground here. So here also you can see that all the forces can travel all the way to the ground. So this is a one elevation, and if you see the whole structure here, let me open the 3D view. So here you can see that this is the elevation. These are the wind columns that the designer has made here. So these wind column, what exactly is being happening here is that he had made this column just like the columns that he has made here. And for bracing, what he has done is that he had provided these cross bracings, and here you can see some of the platform that has been made here. Basically the purpose of this platform is that on the top of this platform a rail is installed so that gantry can be run from all the way from this point to this point. And in addition to the supporting point for the gantry, it also serves as a platform for the gantry maintenance also. That is, in some cases it might happen that we may need to operate or we may need to repair the gantry also. So to repair the gantry crane, they provide a staircase here, and this whole platform is made for the gantry maintenance. So I hope things are now clear to you that what exactly we shall make in our model. The height of this structure is very large, but in our model we shall restrict that to only 8 meters or this height only. So I hope things are now clear to you that what exactly we shall try to accomplish in this lecture, that we shall try to model a structure like this. And I shall also avoid some mistakes that has been done here, like we don't need 1, 2 and 3 bracing here. Only bracing at the starting point and end point may suffice or will do the work. And he has also provided cross bracing here only. He has not provided cross bracing on the internal members. So it is just like we should support, or we should break the or we should make sure that not only the forces along the outer frame are balanced, forces along the inner frame are also balanced, because these are all very slender members that are tied itself to form a composite column, or I should say the built-up column, because composite is the term that we use when we are making a steel beam with concrete, but in that case it is called a built-up column. So in this lecture we shall start our practical modeling. So first of all, save as the model that we had initially worked in the previous lecture. Now we shall go to the plan view and select one portal. Now in this portal, what we can do is that we can just simply select all the members here, go to translation repeat, select geometry only, and select number of steps as, or what we can do is that we can just simply select the nodes that we are talking about, and select this node only, and press Ctrl C Ctrl V and select YS minus 0.75. Select this node and select YS minus 1.25. Select this node here, press XS 1 meter, draw a beam from this point to this point here. Now in addition, what we can do is that we can just copy this node here, draw a beam from this point to this point to general support and remove the support here and select this member here. Go to geometry, stretch selected members to an existing member, left click on this pick member here and then left click on apply. So now we have got this member here. In addition, what we can do is that we can make a system like this here. Go to geometry, add beam by perpendicular intersection. Now we can just select all the members here. Before that, we can stretch this member to this point here. So go to geometry, stretch selected members to an existing member, select this member here and then left click on apply here. Now select all the members here. Go to right click here, left click on insert node and left click on add midpoint. So again draw the members like this, and now we can make a travel path for the forces. As on this junction large amount of forces travel, so we can make these two members as the cross, and we can left all the members like this. And now we can go to geometry, add beam by perpendicular intersection, right click on insert node, left click on add midpoint and then draw the beams like this. So we can cross the starting and end point to consider the large amount of force concentration. We can go to the specification now, left click on beam, start MY MZ and then left click on add here. So we can select all the members here, and in these members only we shall try that only axial forces come. Bending moment may come, but the value should not be that significant. So similarly we can do the same exercise here also. So press Y minus 1.25 and again select these members and select X as minus 1. Draw the beams here like this. We can delete this joint here and we can go to this geometry and stretch selected members to an existing member and then left click on apply here. Now we can do the same procedure here also. So we can go to geometry, add beam by perpendicular intersection and we can select all the members here also. Right click here, insert node and add midpoint. We can select this member, geometry, stretch selected members to an existing member. So now we have drawn the portal truss, and after that we need to assign the properties also. So here we can go to this section database. We can select hollow sections, and hollow sections are of three types: rectangular hollow sections, square hollow sections, and circular hollow section. We can go to the Tata structural steel, and here you shall see RHS, that is rectangular hollow section, square hollow section, and circular hollow section. So either we can draw this portal with the help of pipes, or the circular hollow sections, or square or rectangular hollow sections. So I want to model this with rectangular hollow sections. So we can select this 300 by 200 by 6 and then click on add here and select all the members here. So now the main members have been modeled, but you should notice one thing here. Left click on this member and see the orientation here. So here you will see that this is 300 and this is 200. But if you refer to this manual here you will see that the orientation of members has been drawn like this, and here also it is a square hollow section, but this is a rectangular hollow section. So there is a reason why orientation of member is like this. The reason is that I had already explained in the many lectures in the previous lecture series that this type of arrangement is stronger in this axis, but it is weaker in the across axis or in the perpendicular axis. So when the wind force comes perpendicular to this face here, we should also have some sectional modulus to resist those forces. So to do that, what the designer has did is that he had placed a longer dimension along this and the shorter dimension along this, and this is the member that he has taken as per the for square hollow sections. But it is designer decision that I want to take both the sections rectangular hollow sections. That is also fundamentally correct unless all the forces are balanced correctly. So we can go to the section database again. So under the Tata structure we can select this 150, 156 for columns, 100, 104 for tie members, and 60, 64 for smaller tie members. So we can select these members here, and we can provide this member to these bracings here. And if you are good in basic structural analysis, you should know that the percentage of forces that travel in the diagonal members is much higher as compared to the forces that travel in the vertical members. So we can opt for the smaller sizes for these members here, and similarly we can do the same here also. So we can go to select by missing attributes and missing properties. So we can assign this by missing attributes and missing property, and this member is also missing. So now all the properties have been assigned to all the members here. You can go to select by missing attributes and missing property, Now coming back to this point here, that we can rotate the orientation of these members, but I should say that it's up to our decision only, as this dimension is also not less. That is the size of this members are in the range of 300 but to 200 mm. So we can reduce this, we can rotate the orientation of this member only, because all the top members are tight at all the purlins level, but on the bottom it is not tight. So we can go to commands, geometric constant and beta angle, left click on 90 here. Now if you see the orientation difference here, so here you can see that this is the vertical member and this is the horizontal. That this dimension is 300 mm, this dimension here is also 300 mm. So I hope the things are now clear to you, that how you can model this type of member. Now the task comes that how you can replicate this whole arrangement in all the members here. So as an option, what you can do is that you can just simply delete this arrangement that was drawn previously and go to the translational repeat option. Select Z and the distance was 6.4, so we can select minus 6.4 here and number of steps as 2, and then just left click on OK. So let us check that whether the loading has been copied or not, because loading is also a very important parameter. So here we can see that the loading is also copied, and we shall do the same to these members also. So this tutorial shall also serve as an exercise. Let us say you have got a case where the client doesn't want this I-shaped section here, he wants a truss type section here. So you can refer to this exercise. So how you can save a lot of time of yours in the remodeling by just modifying the existing arrangement. Select Z here, step spacing is 6.4 and left click on 2 here. So now all the middle portals arrangement has been drawn, only the end portals are remaining. So in that case, what we can do is that just select all the members here, press Ctrl C Ctrl V and select Z as -1. So draw a wind column like this, and similarly copy this joint along X as 1 meter. Here you can see that this member is not matching with this beam here. Plus as an additional exercise, what you really need to do is that you need to copy this member along the vertical axis also. So you can refer to this typical arrangement here also, that what exactly he has done. He has drawn a 3-dimensional truss system at the ends. So that we can do also. What exactly he has done is that he has drawn a 3D truss or space truss on the gable ends, but that is not as much required, as the forces on these members are also very lesser. So what we can do in this case is that we can just model these columns as wind columns, as this lattice type, but we can make this section as I section only. That thing is not fundamentally wrong. So press Ctrl C Ctrl V option, press Ctrl C option, select Y as -0.75 and then draw the beams from this point to this point. Geometry intersect, right click here, insert node, and then left click on add midpoint. And then here also draw an arrangement like this. In addition, draw a column like this also. So the only disadvantage of this steel structures is that it takes a lot of time in modeling. So you can see how much effort you are putting here just to follow up with this lecture. But once you have modeled the steel structures, you should be much comfortable with the START software. So this was just a small hack to save your time in the modeling that I had done. You can draw a perpendicular beam from this point to this point so that it serves as a perfect load transfer. And then draw a crosshair. So similarly, you can draw wind columns for these two locations also, and same arrangement can be copied here also. So now this whole all the wind columns and all the gable end arrangement has been drawn as per the portal system. So you can see that how I had managed to balance all the arrangement, and how you can draw the same on your own also. These are just simple things that you need to understand. After that, we need to go to the specification also. So select all the tie beams here. After that, what we need to do is that we need to assign the properties also. So we go to the property page here. Here what we can do is that we can go to the editor file and just remove all the taper section properties, because they are not really required. So they're just adding to the list of your problems. So just select all the tapered sections here and just remove them. We can assign the columns of 150, 156. We can go to select beams parallel to y-axis. Then just select the members, and similarly we can go to select beams parallel to x-axis, and we can assign the horizontal members the property of 100, 104. What we can do is that we can just simply select all the members here. Similarly, we can assign the property of 104 to these members also. So all the time members are missing here, so we can just select 60, 64 and then just assign those members here. Now if we select or check whether some properties are missing or not, so we can go to select by missing attributes and missing property. So no members highlighted red here, so we can display the whole structure here. Now similarly we need to repeat the same process here also. Or what we can do is that we can just simply mirror this whole arrangement onto this point here. So the loading arrangement is also same as far as it is concerned, because it is symmetrical along this axis. So let us check the loading criteria also. If the loading criteria is same, then we can just simply select the center point and then just simply mirror it. So under the dead load and live load it is same. Under the effect of wind load, the loading direction is different, so we cannot just simply mirror this. So we can see here, you can see that it is acting along plus x and it is acting along plus z and it is acting along minus z. So this shall leads to the error in our design. So what we can do is that we can simply copy the type of arrangement that has been drawn here to this area here. Now we shall need to do the same in this gable end also. So to save our time, what we can do is that we can copy the new members that we have modeled, and then we can just do the minor revisions or the minor modifications that are required. So first of all, what we need to see is that what exactly is the midpoint. So here we can see that this is also 19.2 and this is also 19.2. So to be specific, select these two gable ends here, and in addition select some members from here also. So we can go to view and selected objects only. So this is the arrangement that we need to copy, and this is the mirror point, and this is the arrangement on which we need to copy. So as a trial, select these members here and go to this generate mirror option, select plane as XY, node on this plane, and then just left click on copy. So here we can see that these members are correctly copied, and in addition we do need to make this portal here also. So on the top of the this beam here, the loading is same, so we can just simply delete it, and we can copy this whole arrangement here on that point also. So select go to this Control C Control V, select Z as -38.4. So let us check the whole structure here. So now we can see that all the structure has been correctly copied, and the next thing that we need to do is that we need to go to select by missing attributes and missing properties. So here you can see that these members are not assigned any properties. So as we know that these members need to be assigned property of 150, 150 and 6. So we can just copy and assign them properties, and after that again we go to this select by missing attributes and missing properties. So all the properties have been assigned. Now we need to check the most important thing, that is loads, whether the loading is correct or not. So self weight we can assign to view. This is correct and this is also correct. Live load, this is correct and this is also correct. After that we need to check the wind loading arrangement. So this is also correct. So all these things are correct, there is no need to worry about it, but still the modeling is also still not complete. By modeling not complete, what I mean to say is that select this arrangement here. Here we can see that the bracing is only tied along this outer bay. So as an additional exercise, what we can do is that we can also tie the inner arrangement here. So that is correct, and after that we can go to the specification also. Go to the properties here and go to the section database. We can also select CHS, that is circular hollow sections, for the bracing sections. So we can go to this data structure only, CHS, and here we can say let us select 114 and 3.6 CHS. So same thing we need to do here also. Assign the properties also. So now the all the portals are correct, wind columns are correctly modeled, gable end is also correctly modeled, bracing is also correctly modeled, but there is still one thing that is still missing, that is we have tied all the top members, but we have not tied the bottom members. So just imagine this complete length, that is from this point to this point, untied, of 18 meters. That is fundamentally not correct. So what we can do is that we can just simply select these members here and tie the bottom members also. It's like we have been modeling the structure from last half an hour. So it may happen that if you are modeling this for the first time, you may spend even up to 1 hour, but that 1 hour is a very good learning phase for you, so that you can correctly learn how you can model this type of structure. And I seriously hope that when you are modeling the structure for the second or third time, you may end up doing much faster than me also. So we can go to the specification and properties, and we can go to select by missing attributes and missing properties, and we can assign the same property to these members also. So these members will just act as ties, but it is not suggested that we shall tie rafters with the help of these purlins. So what we can do is that we can just select a different member, and actually in design of these members only the slenderness governs most of the times. So we can go with square hollow sections of let us say 100, 104 only. It is already selected. We can go with 80, 80, 3.2. Similarly, we can tie the internal members of the columns also. So these are the small corrections that I had referred to when we were talking about this model. So these are the corrections that we should do. Let us tie the string structure as much as possible. So we can go to select by missing attributes and missing properties. So all the members have been assigned property. Specification, we can select all these members here. It is 80, 80, 3.2. And we can assign the releases to all of these members here. So after that we can go to the load and definition again. Check dead load, self-weight y minus assigned to the complete view. So whenever you add a new member, make sure that you again go to this option so that member is also selected in the self-weight command. Otherwise it do get ignored and you shall get a warning in the output file that the self-weight of the structure is lesser as compared to the original self-weight of the structure. So supporting condition is correct. Still we can select all the joints at the base level and assign the supporting conditions. Specification is correct, properties are assigned, loading is correct. After that, the main elephant that we need to worry about is the design parameters. So in the design parameters, this is the general beam, so that we can assign to all the members here. FILD345000, we can assign that to complete view, or in this case we can assign 310 grade steel, because mostly RHS and SHS are in 310 grade only. And this LZ command is no more valid, because in this case what we need to provide is that we need to provide LY of 4.4. So select all the vertical members. And you should notice that we have not provided any tie to this member here, so that is also not a correct thing to do. So just tie a member here also. Let us design the structure freely. Let us see what exactly is in our pockets. So delete this LZ 8.8 command. LZ 36 is also no more valid. HTTP, we can select hot rolled section, and then we can just assign to view, cause all these sections are hot rolled sections, they are not built up sections. Main 350, yeah, we can assign that to the bracing. That is fundamentally correct. And LX and LY command. Now LX and LY command can be assigned to all of these members here, cause basically what will happen is that purlins do come on the top of these members to support the sheetings. So we can assign LX and LY to these members here. That is not a problem here, but as we are designing these columns, considering this whole passage is free and there is no sheeting here, so we cannot assign this LX and LY to these 6 wind columns here, 3 on this side and 3 on this side. So what we can do is that we can just select all the members here and toggle assign. Again select all the members here and toggle assign. After that, we can assign steel takeoff command to the complete structure, and also we can assign check code command to the whole structure, but with the condition that all of these members, that is tie members that we are talking about, their slenderness should not be an issue. So we can assign main 250 command to these members here. That is, we can allow slenderness of 250. In practical we can go up to 350 also, because these members are serving zero purpose except to tie the these portals. And in addition, we were discussing that we do need to assign ly of 4.4. now you must be thinking why we need to assign that, because we are tying all the members along this length from this point to this point is free, so we need to assign ly of 4.4 and ly of 3.75. so coming back to this command here, so we need to enter ly 4.4 and 3.75. After that 3.75 to these members here. So now we have assigned, and similarly we do need to assign ly of 8.95 to this member and 9.85 to this member. So we can assign ly 8.95 and 9.85. So this was just a shortcut to save the time, and 9.85 we can assign to this member here. So now let us check that whether all the commands has been assigned or not. Main command is assigned lx and ly. Ly command is also needs to be entered for this part here, that is from this point to this point. Ly needs to be entered as per these dimensions, because on the top we are tying at every 1.5 meter, but for the bottom we are not tying the members. So what we can do is that we can just simply select all the members here, portals here. And right now we shall talk only about these portals first of all. So we can select ly 3.75, 4.521, 4.925, 3.927, 4.52 we had already entered, 3.675 we had already entered. So 3.75 we can assign that on the higher side to these members here. 4.521 we can assign to these members here. 4.925 to this member, and 3.927 to this member here. And I shall repeat that we are not providing this ly to the top members, because they shall be supported at every 1.5 meter with the help of the roof purlins. So now lx, ly, lz all are assigned. The slenderness is also assigned, steel takeoff is also assigned, and check code is also designed. So in the next lecture we shall see that what exactly is the situation of our structure, which members are passing, which members are failing, and how we can have an economical design for this type of structures. So first of all, what we need to do is that we need to go to the analyze and then analysis. As the number of members are very high, so what basically start does is that he designed 300 members one by one. In one lot, the start designed 300 members. So first of all, what we can check here is that we can go to the select by specification and all failed beams. So here we can see that only some beams are failing and majority of the beams are passing in the design. So first of all, let us check the behavior of one portal. What are the members that are failing, what are the members that are passing? So first of all, we can check here. So the ratio is 0.692 on the top and 0.5 on the bottom, and here we can see that the ratio is 0.714, and on the top it is 48.4%. And about the members, these members are somewhat more utilized, whereas these members are not utilized. So that we had already discussed that these members, in this member the force travel is very less. So here we can see that only 3.2 kilonewton force is traveling here. Here approximately 10 kilonewton force is traveling, but in this member you can see that approximately 123 kilonewton force is traveling. So that is a lot of force that we are talking about. So here also you can see that approximately 165 kilonewton force is traveling, and there is a negligible bending moment along the minor axis. So that is why it is 11.5.2 section is considerable as per the IC 800, and the ratio is 77.1%. Similarly, we can check the ratios here also, and for this member again it is 72% and it is 56%. Now coming back to the column efficiency, here we can see that the column efficiency is 55% on the outer side and 34% on the inner side. Here it is going up to 83%, and here it is failing in the design. So that we can change the size of this member here. So this member is also failing in the design. So if we see this portal here, let us check the side by side this portal, so that we can see what exactly is the difference in the behavior of this conventional PEB portal, which is made with the help of these I-beam sections. So switch on this bending MZ moment and select 1 times dead load plus live load. Similarly, in this case, we can go to this MZ and select 1 time dead plus live. So you can see the difference in the bending moment here. Here you can see that how much the bending moment is huge that we are talking about. In this case here we can see that bending moment is almost negligible here. Here it is only going like this, so that it is a very negligible bending moment. Whereas in this case the bending moment was going up to this 294 kN here and 751 kN here. Whereas in this case the bending moment is only 19 kN. So all the forces that were producing bending moment producing compressive forces here. So that is the basic difference between this type of structure and in this type of structure. So now we shall check what are the members that were failing in the design. So we can go to select by specification all failed beams. So these members are failing in the design. So what we can do is that we can select all the symmetrical members here. So we have selected this column here and this inclined member here and these two inclined members here. So we can go to the property page, and right now this is 150, 100, 104. So we can assign 150, 150, 6 to these members here, and similarly for this member, that is member number 4. Instead of 150, 156, we can go ahead with 200 by 200 SHS. So we go to the section database, Tata structural square hollow section, and select 100, 104 200, 204 SHS. So 220, 220 by 5 is available. And this member was also failing, it is 100, 104. So we can select 150, 156 for this member here. So let us check that whether with this change whether these members are passing or not. So before we assign the same section property to all the trusses, let us check for this one portal only, and if this portal is correct and all the members are passing, then we shall assign the same property to the remaining portals also. Here we can see there's some sort of instabilities occurring here. So that is why the number of warnings is also increased here. Here we can see that it is saying that member number 224 is slender and cannot be checked for the moment forces. So what we can do in this case is that we can increase the size of this member to 250 by 8, and let us check that whether the stat will accept the size or not. So now if we see the design here the ratio is good, that is 71%. This member was changed, it is also passing in the design, and both of these members are again passing in the design. So if we go to the select by specification and all failed beams, you will see that all the beams here are at least passing in the design. So as a next exercise, what we need to do is that we need to assign the same properties to these portals also, so that once for all our design for the complete structure is correct and we are standing on the same ground for all the members. See, design is an iteration process. It is not something that we do in one go. So now we have changed this member also. After that we do need to change this member here and all of these members here. So let us analyze and design the structure again. So we can go to select by specification and all failed beams. So here we can see that all the beams here are passing in the design. After that we can check the behavior of the wind columns and gable end sections also. So here if we check the ratio, it is going up to 55%, and on the top it is going lesser, that is only 33%. Here also the ratio is very less. So all these members are much, we can say that these members are over designed. And if we are talking about these members here, so here also there is a scope of improvement, that is we can reduce the size. So concluding this lecture, first of all I shall repeat the important point that you have now understood what exactly was the bending moment diagram system here. If you want to shear force, if you want to see the shear force here also, so this is the shear force diagram. So the importance of this type of arrangement is different, and importance of this type of arrangement is also different. In this type of arrangement, fabrication cost is quite high, and the fabrication time is also quite high, whereas in the conventional system of fabricating eye girders, the fabrication cost is also somewhat lesser, and the time is much lesser as compared to this type of system. And we have concluded that how you can design the bracings here. So here also you can see that the bracings are going up to 71% utilization. Here also it is going up to 86% in utilization. So we can check the tie members also. So here we can see that they are only governing in the slenderness, that is the allowable slenderness we have assigned us in the range of 250 mm, so it is going up to 205. So you can reduce the size of this member, and we can see the total weight of the whole arrangement also. So we can go to the steel takeoff. So total weight is coming out to approximately 50 ton. So as a simple math, what we can do is that we can calculate the size of this shed here. So it is 36 into 38.4. So it is approximately 1382 meters square, and we can multiply it by 11 to calculate approximate square feet. So this structure is approximately 15,000 square feet, and the total weight is coming out to be 50 metric ton only for the structural steel. We can add the purlin weight and connection weight, so it will go up to approximately 55,000. So 55,000 divided by 15,000, it is coming out approximately 3.67 or approximately 3.7 kg per square foot. So it is almost on the higher side, because the projected thumb rule or the projected weight of this type of structure should not be more than 3.2 to 3.3 kg per square feet, because there is a much scope for optimization here also. That is, here we can reduce the size of these members. That is, this ratio is going only up to 55% and 54%. So as a trial, what we can do is that we can change the size of this member from 300 to 200 to, let us say, 300 to 156. So let us analyze the structure again. So here we can see that the ratio is still somewhat on the lower side. It is only 58%, but the bottom member may fail. The bottom member is also passing in the design. Let us have a look at the total steel takeoff again. So it is now reduced to 48.4. So we have reduced the weight to 1.5 metric ton just by reducing the size of this member. Similarly, we can reduce the size of this member more also. So it's all up to you that how much permutation combination you can have, or how much permutation combination you can do. Like, we can reduce the size of these members also, 150, 156. So for these wind columns, we can have a separate size of the members. So the projected weight, or what you can do on your own, is that, as per my judgment, you can reduce this weight to 400 kilonewton or 40 metric ton also. So that you can do on your own. That you can try various permutation combination. You can try reducing the size of these members also. That is, this member is right now 60-64. You can reduce it to, let us say, 40-43 or 40-44. So all these steps can lead you to huge savings. For example, let us say if we reduce the size from 60-64 to let us check 40-44. So we can go to select by specification and all failed beams. So some of the beams are failing in the design, but most of the other beams are already passing in the design. So here we can check what exactly is now the weight. So the weight has now somewhat same because this member is not causing much difference. It is only 7.7 kilonewton or 770 kg. But here we can see that this is the main member, 300-156. Its weight is approximately 17.5, and 150-156. Its weight is also quite high. So you can reduce the weight of these two sections, and you can have a lot of savings also. So you can target it to approximately 44 to 43 metric ton, because in addition we shall need the 10% to 15% margin to account for the wastage, and to account for the connections weight, and to account for the base plate or stiffeners or all the connections that we do need to assign. So for a record, I shall attach the stat model of this file also. I shall change it to 6064 only, so that the model in your record should be correct with all the beams passing. So I hope you have learned that how you can model the truss type of portal arrangement, and how you can calculate the forces, how you can model it, how you can analyze and design it, and how you can see the results, how you can calculate a total weight, what are the thumb rules regarding the weight of the structural steel structures, and all those things. So it's all up to you and all up to your practice, that how much practice you do, and what are your observations. And I shall suggest you to read some good structural steel books, so that you can learn much more about the steel structures. So we can go to select by specification and all failed beams. So no beams have failed. So I am attaching this model in your lecture series, so that you have a correct model in your records. And there's this one more thing that I was just thinking about it, that you should also know. Like when we are applying this loading here, the gable end forces, the gable end forces are 7.03 kilonewton meter. 50% needs to be applied on these members also. So that I had missed in the initial analysis, but I am just saying this for your records, that you should not do anything incorrectly. That the 7.03 divided by 2, that is approximately 3.515 kilonewton meter per meter UDL shall be applied on this column here and this column here also. Similarly for other wind case, for example here also. So 7.03 divided by 2, cause the effective span of this arrangement is only up to this point here. So on this column basically the loading are biaxial, that is from this direction also and this direction also. So this was just a small addition or alteration that you do need to do on your own for the correct analysis and design. So see you in the next lecture.